Have you ever stopped to think about how the internet doesn't just, well, collapse? I mean, every single second, millions of us are shopping, banking, and posting all at once. It should be total chaos, right? But underneath it all, there's this incredibly elegant set of rules that keeps everything in perfect order. So today, let's pull back the curtain and look at the invisible architecture that actually powers our digital lives.
All right, let's start with a classic. Picture this. You've been waiting for this super rare, limited edition thing to drop. You see there's just one left in stock. Your heart's pounding, you hit buy, but at that exact same millisecond, someone else on the other side of the planet does the exact same thing. So who gets it? What's supposed to happen? This is the kind of problem that computer systems have to solve constantly.
Because if the system isn't built to handle this exact moment, a lot can go wrong. And we're not just talking about who gets the item, we're talking about the entire system's integrity. Let's walk through just a few of the nightmares that could happen. First up, the most obvious mess. The store sells that one item to two different people. Both of you get a confirmation email, both of you get your cards charged, but there's only one physical item. The store's inventory now says -1, and you've got two very unhappy customers on your hands. Or what about this scenario? The system takes your money, which is great for them, but before you can actually update the inventory to reserve that item for you, it glitches. So your money's gone, but the item is still listed as in stock. And yep, you guessed it, someone else comes along and buys it. You are out of cash and totally out of luck. And then there's the absolute worst case scenario. These two conflicting requests confuse the system so badly that it just throws its hands up and crashes. The whole thing goes down. And when it finally reboots, the data is a complete disaster. Maybe your payment is half processed, the inventory count is garbage, nobody knows what really happened. It is pure digital anarchy. So how do we prevent this kind of chaos? Well, thankfully, there's a hero in this story, and its name is the transaction. This one simple, powerful concept is what makes our digital world reliable and, predictable. So what is a transaction? You can think of it like a promise. It takes a whole bunch of different steps and bundles them together, saying all of these things need to happen as one single unbreakable action. It's not a list of separate things to do, it's one logical event. The perfect example is a bank transfer. To you, it feels like one thing, right? You send money, they get it. Well, the system sees it the same way. Taking $500 out of account A and putting $500 into account B aren't two separate events. They are two halves of one single transaction. If either part fails, the whole thing is just canceled, like it never even happened. The money can't just disappear into the ether. Now, for a transaction to be really trustworthy, it has to follow 4 incredibly strict rules. And you can think of these as its superpowers. They're known by the acronym ACID, and they are the secret sauce that makes our digital world function. First up, we've got A for atomicity. This means the transaction is all or nothing, plain and simple. In our bank transfer, either the money is successfully taken from account A and successfully delivered to account B, or it's as if you never even hit the send button. There is no in-between state where the money is just gone. Next up is C for consistency. This is the rule keeper. It makes sure that a transaction can't break the database's own rules. For instance, a transaction can't just invent money out of thin air or let an account balance go negative if the bank doesn't allow that. The data has to make sense before, and it has to make sense after. No funny business. Then we have I for isolation, and this one takes us right back to our online shopping problem. Isolation basically puts each transaction inside its own soundproof room. Your buy transaction and the other person's buy transaction can run at the same time, but they can't see or mess with each other's work until one of them is completely finished. This is what prevents them from tripping all over each other. And finally, D for durability. This means once the transaction is successfully completed, or committed as they say, its changes are permanent. They are set in stone. Even if the entire server farm loses power 1 second later, that finished bank transfer, or that successful purchase, is safe. It'll be there when the system comes back online. Okay, so we've got these amazing, reliable ACID transactions. That's great. But modern systems have to process thousands, even millions of them, at the same time. This is what's known as the concurrency challenge. How do you get all that speed without sacrificing the safety that ACID gives us? And this slide really shows the dilemma perfectly. On the left, you've got a serial schedule. Transactions line up nice and neat, one after the other. It's perfectly safe, totally isolated, but man, is it slow.
On the right, you've got a concurrent schedule. The system interleaves the steps from different transactions to save time. This is way, way faster. But it's also like the Wild West if you don't manage it carefully. So what's the big deal? What actually happens when we just let these transactions run wild and interleave their steps without any rules? What kind of problems can pop up?
Well, here's a perfect example. It's called a dirty read. Check this out. Transaction T1 updates a piece of data. Let's say it changes an item's price. But before T1 is finished, before it's committed, transaction T2 comes along and reads that new price. But what happens if T1 fails and has to roll back its change? Well, it's too late. T2 has already made a decision based on a price that never technically existed. It read dirty, temporary data, and now its own results are totally unreliable. So the ultimate goal here is to get the blazing speed of a non-serial schedule, but with the rock-solid safety of a serial one. And to do that, to bring order to all this chaos, we need two key ideas: serializability and locks. Serializability is basically the holy grail of concurrency. It's a guarantee. It says that no matter how you jumble up and interleave the steps of all your transactions, the final result will be exactly the same as if you had just run them one by one in some order. We get the speed of doing things all at once with the correctness of doing them one at a time. It is literally the best of both worlds. So how do we actually enforce this guarantee? The main tool for the job is something called a lock. You can think of it like a talking stick for a piece of data. Before any transaction can read or change that data, it first has to ask for and acquire the lock. And while it's holding that lock, no other transaction that might conflict with it can touch that data. And there are two basic types of these locks. First is a shared lock. This lets a transaction read data. Think of it like a library book. Lots of people can be reading the same book at once, right? So multiple transactions can hold a shared lock on the same item. But then there's the exclusive lock. This is for when you want to write or change data. And just like you can't have multiple people writing in the same book at the same time, only one transaction can hold an exclusive lock. So, many readers or one single writer. Now, systems use very strict rules for how to use these locks. The most famous protocol is called two-phase locking. It's actually pretty simple. In the first phase, the growing phase, a transaction goes around acquiring all the locks it needs. It just collects them. Once it starts the second phase, the shrinking phase, it can only release locks. It can't go back and grab any new ones. This simple rule, collect everything you need, then start letting go, is powerful enough to guarantee serializability. Okay. I know we've gone deep into some pretty technical stuff here. ACID, serialization ability, locks. But let's zoom all the way back out and talk about why this is all so incredibly important in your actual day-to-day life. Because this is the invisible engine that makes the entire modern world run. The reason your bank balance is always correct, the reason you actually get the concert ticket you paid for, the reason an online store doesn't sell the same shoes to 5 people, it is all thanks to these principles. Every single reliable digital service you use, without exception, is built on this foundation. And that really leaves us with a final thought to chew on. As our world gets more connected, as data moves faster and faster, the challenge of maintaining this perfect, elegant order only gets bigger. So the next time you click buy or transfer some money, just take a second to appreciate the incredible, invisible dance of transactions and locks happening behind the scenes, working flawlessly to keep your digital world from falling into chaos.